The talk is going to be a very exciting talk on machine learning. Take it away.
Yeah, of course. Check. We're good. So this is what you can think of this doing is the Haskell as a basic model type where you can run it and do a backpropagation gradient. You can chain models very naive. So this is a naive implementation. You can chain them by chaining the running function and chaining the backpropagation. This is, by the way, the entire backprop algorithm. So this is what you might think of doing this. So and also if you use a AD library, you can even make it easier. The model is just basically a basic function. So all it looks so far so good at the simple, naive level. Your loss function basically values the loss and then gets double to optimize against. So once you get that, you differentiate the optimizing the double and you backpropagate. So far so good. You can chain this pretty well. It's very composable, very beautiful. My first attempts were like this. So it's a solved problem, right? Haskell is conquered machine learning. Actually not. So let's add parameterized initialization. Each parameter has to be initialized somehow. So when you make your model, you have to say how you should start your model with the basic parameters. More features, we want to regularize, so that can look like a P to double function that gets you a differentiable running total of things to optimize against. And kind of showing you that this is getting very it's doable, but it's getting more and more layered and more complicated. And also modern models, they add noise and weights. Maybe when we want to like add a nudge to run during training to nudge the parameter a bit, we want to add random noise or do random scaling. But this function does not compose, so we can no longer write chain anymore. We can't compose these anymore. We have to like, maybe we can chain them in a gadget with like extensible variables, and that could work. But the more we try to fit this into this box, the more ugly and bad it gets, unfortunately. So this doesn't work. And the problem is that most libraries, and even Python these days, have the same issues. So models have to declare all the capabilities up front, all the noise, all the regularization, all the parameterization, all the backprop functions up front. Every model has to know about all the capabilities, and the composition is inherently existential. So models have to be essentially composed with their internal functions hidden inside a chain of hidden variables with dynamic dispatch. There must be another way. There has to be another way, right? And that's why I'm here. So what do we actually need? Like, what are we looking for? We want to selectively integrate actions of multiple capabilities, parameterization, backprop, regularization, all that stuff. We want to run these in different contexts, right? When we're training, we want to have regularization and noise. When we're evaluating, we don't. When we're initializing, we only care about new parameters. So we have a lot of actions. We want to defer them to runtime. And we want to compose actions of varying capabilities, right? We want model A and model B to compose, and their capabilities will merge together in the sort of union of capabilities, right? So if one model has regularization, the other doesn't, we want them to compose to have a big model that does do regularization. And does this look familiar with another like space of Haskell research? It's in the title. This is actually basically extensible effects, right? So everything we talked about seems to be perfectly fitted for extensible effects. And as far as I know, there's no other research combining extensible effects with machine learning capabilities like this, which I think is interesting. So come with me on more of a exercise of the imagination. The type signatures coming up are not exactly going to be, I don't expect you to understand all the code, but imagine what if we did this? What if we put everything together? What do we gain from this, and what do we learn? And where does this open? So we do know that thanks to Jesse Siegel's great doctoral thesis, that AD itself is an effect. So if you use the effect library, you can have variables that you can differentiate. So assigning variables that you can differentiate and tracking them throughout the life of a program, of an F program, is very doable and very efficient. And Jesse goes through multiple ways of doing this in an effective way. So backprop itself is already an effect. So the main machine learning thing, backprop, already solved. What else can we do? We can add parameterization as an effect, right? Maybe an effect could be initializing a parameter, initializing a new matrix or a new vector. It can be initialized under namespace as an effect. So as an example of how you could write this as a library, let's say your model is just a function from A to B, a Kleisli arrow in the effect monad. Then you have a model already that does like a feed-forward neural network. You compose them very simply by just having layer 1, layer 2, layer 3, feeding the values through each other. So this is like a nice way to compose them, and there's no longer any mixture of, it's a monadic Kleisli arrow, is very clean, and you look at it and see it's very clear where the data is flowing. So this is nice, but yeah, so we can run these as eliminators, and the idea is that when we train a model, we eliminate the F. When we run a model, we eliminate the F with different handlers. So in training, we eliminate them with our training, our noisy handlers, and we run them with our no-op handlers, for instance. So with no noise, no anything when we're running a model. And that's done by just handling the different dispatches. So let's look at what we can gain out of this. So what actually happens when we do this? Well, how does our mind open if we do this? So all models end up being just Kleisli arrows. So all machine learning models, from the biggest LLMs to the smallest iris dataset classifiers, feed-forward neural networks are just classes, arrows, and F. And models declare their effects. And when you combine models, the type checker combines effects by just combining type class constraints. And if we put bvars, the differentiable values, so think of bvar as a differentiable value in effects, what does this give us? So what if we had bvar, a state of bvar, or a reader of bvar? So I'm gonna kind of give you my Hamilton Bridge moment. This is my story. I was walking down the park and I was thinking, wait a minute. What is writer sum bvar double? Does anyone have an idea of what this might be? So imagine that your effect is just a writer of a summed differentiable value. This actually is regularization, right? So you have a running total of differentiable values, and every model can write to the writer, because the bvar is tracked as a derivative. So if every model just writes and tells to this running total, that writer, that log, is also differentiable as well. So by just using normal Haskell things, these Haskell modular transformers and effects correspond to machine learning properties that we hadn't explored before. So we have a regular effect. We can have like a tell of organization. We can choose to regularize an L2 or an L1. And in training mode, this is a writer tell. And in inference mode, it's just a no-op, right? We don't care about regulation in inference. So you see that these normal Haskell concepts that we've been using all along correspond to these ML effect concepts as well. So yeah, so if we tell from the parameters, we get organization. If we tell from an actual like output of a model, we get layer normalization. So we start matching all of these exotic terms that they invented in these ML papers are just basic writer or basic modular transformer concepts in Haskell. And it's basically a zoo of different things that you can find in these papers. Stochastic perturbation, noise injection is just adding a value, but we can get injection of multiplicative noise, which is what dropout is, and other terms like that, are a transformation on differentiable values. So I'm basically condensing like a lot of these terms are, if you read the ML model, there's a billion terms that they give out names, things like dropout. All those are condensed to basically very simple Haskell concepts, as long as we have differentiable effects in our stack. And we can have a batch effect, which is not another major concept in ML. We can have reader-like context, which means we can thread things like annealing parameters, training rate schedules, different hyperparameters. So I'm giving these as like very ridiculous words, but all these are real words that they use in ML. And they correspond to this basic Haskell reader, writer, state type of values. We can even thread arbitrary signals from runners for observability. So the basic idea is that all of these zoo of effects, if we imagine them in a better world, they're just normal extensible effects. And they combine very well in Haskell. I've run this, I have a library implementing this that I hope to release soon. But because we can now throw in derivatives in our effects, all these effects correspond to interesting ML concepts. And I leave your own journey, hopefully it opens your mind to exploring these concepts under this new framework, this new idea that we can do. These code snippets, I've implemented them in CPU. It's mostly conceptual. There's no attention to benchmarks just yet, but hope I can find meaningful benchmarks to do with just CPU and GPU programming. And future work, I hope to polish and finish up the library, mostly just to have a nice declarative semantics. And I want to basically classify all these ML primitives across the thousands of papers as just basically normal Haskell reader-writer effect patterns. And I believe it is possible. We must believe. and maybe even GPU programming as sensible effect as well. Yeah, that's for questions. I write a lot on my blog about this stuff, so if you follow blog.jlee.im, you can follow along with my adventures.
Questions?
Is this not published somewhere? Because your Hamilton on a bridge moment seems to be valuable enough to be written up.
It is in progress. I have a paper, but it's not published yet, but it's in work, yes.
That we're using effects to build up these models, is there enough structure there that we could also interpret these into some kind of representation that then gets pushed into some other efficient library for doing these things? Or?
Yeah, the main problem is that effect monad, the bind function is like a Haskell function. You can only go so far. By picking the right new type writers, you can make certain things no-ops in Haskell, but as long as you're in a monad, you're kind of stuck with the Haskell function as like the determining thing.
There's been some other talks during ICFP on similar issues and not using monad as the sort of underlying interface for these things, like using arrows or categories, which should give you a little bit more access to that that structure, I think.
Yeah.
I don't know. I'm just an everyday Haskell programmer. I don't know.
I think actually like the set of functions you actually need to write are very small, so it's very doable, I think, to actually like defunctionalize to a level that can be compiled effectively.
All right, let's thank the speaker again.
Thank you.